maybe in the panel session, we can come back to these things.
Yeah, great.
So thanks very much, Eric.
Thank you.
So going to move to the next speakers, Dimitra Salmanidou from UCL. Are you there?
Yes, hello, can you hear me?
Hi there, yeah. Are you ready to share screen?
Yes, I'm trying that now.
So Dimitra Salmanidou is Senior Research Fellow in Statistical Sciences, UCL. And she will be talking on uncertainty quantification workflows for high-resolution tsunami hazard prediction in North Cascadia. Okay, please go ahead.
Yeah, so hello everyone. I'm doing my postdoc with SARS at UCL, and my work involves the numerical modeling of tsunami hazard and uncertainty quantification methods. And in this talk, I'm going to describe about some workflows that we followed to predict tsunami hazard in North Cascadia. Before starting, I would also like to mention the uncertainty quantification of multi-scale and multi-physics computer models project with the Alan Turing Institute, which really helped to materialize this work. So in tsunami hazard, there is in general a need for high-resolution modeling to inform, for example, disaster mitigation plans. And this often comes in contrast with the need for small computational times that might arise from limited computational resources or for other reasons. Depending on the choice of the fluid dynamics, the numerical schemes, or numerical meshes that we're using for the modeling, the computational codes can be quite expensive. This makes uncertainty quantification methods more difficult because numerous scenarios are needed. So a prominent solution for that can be statistical emulators, which form stochastic representations of the deterministic response. They can run once built almost instantaneously, so they can provide with probabilistic predictions of the output given some specific input. So the region of interest is the Cascadia subduction zone. It's located in the US Pacific Northwest and Southwestern British Columbia. It's a very long zone that falls in the interface of the subducting Juan de Fuca plate and the overriding North American plate, and is capable of great earthquakes. The last great megathrust earthquake in the region has been probably the 1700 earthquake, which had a magnitude of 9. The timing of the earthquake has been inferred from Japanese records of a tsunami, which was recorded at 7 shoreline sites in Japan, but it was considered an orphan tsunami until the Japanese scientists made the link with the North Cascadia. So after a few centuries, the stakeholder interest in the area has increased because there is a large exposure due to the urbanization, and especially in the city of Vancouver and also in the city of Victoria in British Columbia and Canada. So the objective of this study was to build statistical surrogates for tsunami hazard prediction in North Cascadia. And yeah, so the workflow can be divided in 3 parts. The first part involves the setup of experiments, how to proceed with a study. And it's quite important part because it can have an impact on the whole study. The second part is the study design and the numerical experimentation. And the third part that I'm going to discuss about is the statistical emulation and finally the hazard prediction. So all these parts are interlinked with each other, and I'm going to discuss them in more detail in the next slides. So when it comes to experimental setup, there are lots of aspects to consider, such are the data that we're going to use. And for this case, we use the digital bathymetry and topography of the area. And but this may come in many resolutions, in many sizes, in many formats. So a uniform data set is needed in order to do the modeling, and a lot of merging and interpolation falls into these states. And the other aspect is the grid. So we need the grid to be very finely resolved in the area around Victoria City, and where we want 30-meter resolution. However, we cannot afford to have such a grid all across the domain, because it would be huge, and probably the simulations would crash. So for this reason, we are using some algorithms that were developed by a colleague of mine, Devares, and I'm going to give the reference later. The other aspect that we need to consider are what kind of parameters we are going to use for the modeling. And for this case, we're using a cosine function to describe the shape of the deformation. And we're also using the time of the deformation. The ranges of the parameters are also quite important. Very small ranges, for example, might not capture well all the trends of what might happen. And another aspect finally to consider are the model choices. So for this case, we're using Volna. It's a nonlinear saltwater equation solver, which works well on unstructured grids. And for this reason, we can capture well the complex topography of the region. For the design, we're using mice, and for the statistical emulation, we're using MGP. So in the core of the design workflow and experiments lies mice. Mice is a sequential design algorithm that adaptively selects the input values at which to run Volna in order to maximize the expected information gain over the input space. So we have an LHD that gives us some candidate points, and then we feed a GP to the inputs and outputs, and use a mutual information design criteria to find the next set of runs. So as we start with mice, the output are the input values. And in this case, these are the deformation parameters. So we build the deformation shape, and then we feed this in the tsunami model to do the numerical modeling. And from that, we extract the maximum tsunami elevation at one location, which is close to the city of Victoria, and which we consider to be informative for the design. And this location, the results of this location feed back to mice, and we continue the process again. So this is a circle that iterates for 12 times, and each time we choose to run 5 simulations. So in total, we have 60 simulations that run on HPC, and the workflow has been automated. So here I'm going to show an example scenario. We have the tsunami trough that enters the strait, followed by tsunami crest. The wave arrival is about 80 to 90 minutes after the wave generation. And what we are looking for to extract is the maximum tsunami elevation at the cell centers of the grid. And in this case, we have 125 locations, 125,000 locations, sorry, for which we want to build the emulators. So for building the emulator, we're using a multi-output Gaussian process. And the benefit of this process is that we can build several emulators in parallel, assuming that each independent emulator is fit to its output. And the process can be distinguished in 2 parts: the fitting and building of the emulators and the prediction with the emulators. So the first part involves the training data. And in this case, we have 60 runs again. The input data of the training runs are the deformation parameters, and the output is the maximum tsunami elevation of the cell centers. And we also have to make some model choices, such as what is the kernel function that we're going to use, or what's the fitting method. And after we make these choices, we validate the code using live-on-ad diagnostics, which may lead again to the beginning of the process, trying to find the best kernel functions. And then we proceed to the prediction part. And for the prediction, we use 2000 deformation scenarios. And we can, depending on the knowledge of the system, we can use the input parameter distributions to express what we expect the system to behave like. And there are two ways of representing the results. The first is about plotting the histograms of these predictions at each location. And the second way we use is providing with probabilistic tsunami hazard maps using the percentiles of the mid predictions. So such a hazard map based on the 75th percentile of the predictions is this one. And we see that given these parameter choices, the tsunamis mostly vary between 0 and 1 meter, and also 1 to 2 meters. So regarding computational times, you can see that the numerical experiments are of course the most expensive to run. And the highest cost comes from Volna, which runs in 279 to 288 minutes in 4 GPUs. All the experiments were done on the CST3 cluster of Cambridge. And if we think that we have 60 simulations, then that becomes automatically 280 hours. On the statistical part, each emulator builds between 2 to 4 seconds approximately. So that means that for 125,000 emulators, we have 104 hours of fitting if each emulator takes about 3 seconds. The prediction part is quite fast, and we have almost 19 minutes for the predictions. So to summarize, we used the sequential design algorithm to for the adaptive selection of the computer experiments, and we built 125,000 emulators to study onshore tsunami elevation. We check results from 2,000 scenarios of varying seabed deformation to produce probabilistic tsunami hazard maps for Southeast Vancouver Island. We observe that the highest computational costs are also expected in the training part. So to expand this study to more regions, more dimensions, we will need more code optimization, especially when it comes to the parallel process, but also more computational resources. And here are the references for this talk. Thank you very much.
Thank you very much. I didn't see any questions on the chat or in the Q&A. I might just ask you something. You're using statistical priors. So these are just simple statistical functions like gamma, beta functions, and so forth. Did you think about using more physics-based priors?
So the input parameters that I'm talking about are more physical parameters for the numerical modeling. And for the statistical priors, I'm using MLE.
Okay, okay.